Hi there guys, this is 15I and 15J. The two exercises go together to complete the book for the HLAI Oxford IB book. This is about graph theory for weighted graphs, so we're still talking about weighted graphs here, and both of these exercises look at algorithms for the traveling salesman problem or salesperson problem. Okay, so the TSP. Now, the first of these exercises looks at the algorithm for finding an upper bound for the problem, and the second of the exercises looks for the lower bound of the problem. In fact, there is no algorithm for the perfect solution to this, unless you go through many thousands of combinations, and that becomes computationally impossible. Okay, so let's just talk about this briefly. Here's the first example. The first example starts by asking us to make a complete graph for this network here, and we'll talk about that in a second. But just before we do that, of course, we've done the Chinese postman problem beforehand, and now we're doing the traveling salesman problem. And the Chinese postman problem was about visiting all of the edges. So that was when we needed to make an Eulerian circuit, if we were coming back to the start, or if we were starting and finishing at different places, or an Eulerian trail. That was all about the degree of each of the vertices. Okay, now when we were making Eulerian circuits or trails, we didn't care about the lengths on the edges. That was only when it became the Chinese postman problem. Okay, but if an Eulerian circuit existed, then that meant to say that we could theoretically start and finish at the same place. Now, we've got a similar sort of idea for this one, but this is called a Hamiltonian, and the language is slightly different here. This is talking about a Hamiltonian cycle or a Hamiltonian path. So what are we talking about? We're saying, let's start at A, and let's visit all of the vertices, and then return to A. That would be a Hamiltonian cycle. For example, A, C, D, B, A is a Hamiltonian cycle which exists here. Okay, now a Hamiltonian pathway might be A, C, B, D ending up in a different location, but in general, we don't care about those for the traveling salesman problem. We sometimes did with the Chinese postman problem. Sometimes we were allowed to finish in a different place. It depends on the context of the question, but in general, you're going to be asked mostly for both of these things to finish at the same place as you start in terms of the questions you're going to be given. Okay, so we care about making Hamiltonian cycles, but Hamiltonian cycles don't care about the weightings. So we have to factor in all of the weightings on the edges. Now, in order to make a Hamiltonian cycle where we can consider lots of different routes, we're going to need a complete graph, and that's called the classical traveling salesman problem. Now, we can make this a complete graph by basically adding in an extra length here, the extra length which is missing, which is A to D. Okay, so our first task is going to be, when applying any of these algorithms, is to change this into a complete graph. And instead of having a graph of all of our distances via the direct routes, what we want is a graph of the shortest routes between each of the locations. So what are we talking about here? We're talking about this, even if I put this in, this extra length here, and even if I said that this extra length is, what's my shortest distance there, 105, that's not going to be the graph that I require. The graph that I require is a complete graph which has the shortest distances between each of the edges. So for example, the C to B will actually have the weight on of 95. Okay, I'm going to do this question in a minute, so I'll stop talking about that, otherwise I'll just repeat myself. Okay, now a complete graph, you need to know about what a complete graph is as well. I was meant to say complete. A complete graph is, like, for example, K4 would be every vertex attaches to every other links to every other vertex. That's K4. I was going to do it for K5, and you don't need to be aware of K4, K5, the notation, but it's I guess it's kind of nice to know. So here we go. This would be our graph for K5 in this case. This would be a complete graph for K5. Okay. So it says this graph shows the direct bus connections between 4 towns. So you can see that A and D are not connected directly in this case. It says the weights are the times of the journeys in minutes, and the buses travel both ways along the routes. Construct a table of least distances to show the shortest journey times between each pair of towns. Assume that there is no need to change buses on any of the journeys. Now, what they're asking you to do here is to create a complete graph through a table. We can make this up in a moment as well as another graph too. So we need to do this before coming into our algorithms for completing the traveling salesman problem. So if we look at A, for example, so we're looking at A is connected both to C and B directly, so C and B, but the shortest route to D, obviously that doesn't exist, is this route here of 45 plus 6 is 105. Now, it's possible that it could have gone like this as well, obviously, if that length was shorter in the middle, for example. But you can see how this is being constructed here. Now, B is connected to all three, and I think B is connected, and none of them, by the way, are connected to themselves. And basically, if I've got these answers, I can complete them on the other side as well. So B is connected to C with a minimum length of 95. So that's this way here. So that's 95 and 95. And D is connected to B there as well with a minimum length of 70. Okay, and then C is connected to D with a minimum length of 60. Okay, and then of course we can copy those things across. That's going to get a little bit messy when I fill that in, but you can copy those things onto the other side as well. Now, this table here is going to create a complete graph for us. So now we have the situation where we can now say we've got, let's just do it over here, we've got A and B and C and D. Now the complete graph is going to look something like this, and we can put all of those weights on the graph as well. If we want, we can put one of those around the outside. For example, it doesn't really matter. Okay, maybe that's slightly neater to put in your numbers. Now, A to C, we can put in as 45, and A to B is 50, and A to D is now 105, and B to C is 95, and C to D is 60, and B to D is 70. Now, that's a different graph to your original one, but what we've created there is a complete graph. We've created K4, in fact, but a weighted version of that graph as well. Now, we need to be able to go from this to this in order to use our algorithms, or potentially from this to this in order for us to use our algorithms. Okay, so this is a really important skill, to be able to make a complete graph by just looking at a graph which talks about doing the shortest distances. This is still a completely valid graph. It's just describing different information. It's now just saying, how are these things connected in their shortest distances? It's not now talking about there being direct routes between those places. So it's a different graph, different information, but what we've done is created a complete graph showing all of the shortest distances. Okay, really important. So let's go into looking at the traveling salesman problem then with a bit more depth. Now, basically, there's a couple of investigations there which you can have a look at, and of course, those investigations are answered in the teacher notes. But here it says the classic traveling salesman problem, TSP, is to find the Hamiltonian cycle of least weight in a complete weighted graph. Okay, now we're not necessarily doing that. We're doing a practical traveling salesman problem. So Hamiltonian cycles aren't necessarily going to exist. Remember, that's visiting all the vertices once, which in a complete graph you could do, for example, just by going around the outside. That would be a complete graph. That would be a Hamiltonian cycle. And there would be many Hamiltonian cycles there because each option allows you to go wherever you want. Now, the fact is, though, that you're unlikely to be given that situation and you're going to be given a graph which is not complete. So you will need to make it complete in order to use the algorithms. Now, the practical traveling salesman problem is to find a walk of least weight that passes through each vertex of a graph, starting and finishing at the same vertex. In this case, so that's creating a cycle. In this case, the graph need not be complete. Now, in fact, sometimes your starting point might not be the same as the end point. So it depends on the context of the question as to what they're asking, in fact. Okay, but more likely than not, you will be asked to finish at the same place as you started. Okay, and for that we have algorithms. So finding an upper bound. So there is, in fact, when you imagine that you suddenly have bigger complete graphs, say you have a complete graph of 10 different locations, then you have many different routes to complete that. In fact, you're starting off with 9 different routes from the first node, and then you've got after that, after you've gone, say, from A to B, then you've got 8 different routes to go there, to go to another node, and so on. So you're going to have 9 factorial different routes. Now that gets really large really quickly. Let's have a look at 9 factorial. 9 factorial, let's see if Google can do that. There we go. So we've got, just with 10 different locations, we've got 362,880 different routes to consider. So you can see that in a big network, say for example, we have, 100 different locations which we have to visit, suddenly this problem is massive. It's vast. So in fact, this is a problem where we don't know the optimal solution because there are just way too many solutions to check here. There are way too many different pathways to check. So the best that we can do is say, well, here's a pretty decent upper bound, and here's a pretty decent lower bound, and we're going to trap our answer between the best lower bound we can find and the best upper bound which we can find. So the best upper bound is going to be closer in, and the best lower bound is going to be higher up. So we're going to try and trap the total length of this journey to make a pretty reasonable length of journey, which is likely to be near to the best journey possible. Okay, well, you can imagine that this is really important in terms of maybe Google Maps, for example, trying to make the shortest journey when there are many thousands of different routes which can be taken. Okay, so let's have a look at one of the problems then. So let's have a look at the best upper bound algorithm. So this is called the nearest neighbor algorithm, which basically does what it says. It basically goes to the closest neighbor each time in order to complete a circuit. And in order for you to do this, you're going to need to have a complete graph, which is based on the shortest distances, which is what we've just done in the previous example. So the algorithm has 2 stages. 1, if the graph is not complete, create a table of least distances or weights showing the shortest route between each pair of vertices. That's what we've already done. 2, use your table or equivalent graph, choose a starting vertex. Now, if we have 100 vertices, again, you can see that You're only going to have to do this 100 times, but we're going to be told which vertex to start with. So choose a starting vertex and move around the graph, always going to the next vertex that has not already been included in the cycle, and the next nearest one, it says there. So the nearest vertex has not already been included in the cycle. Once all the vertices have been visited, the shortest route back to the starting point is taken. Okay, now potentially the shortest route back is this huge, vast distance for that last option, and suddenly you have a terrible upper bound. But it doesn't ask us to repeat this, in fact. You would think that part 3 asks us to then choose another starting vertex. It doesn't do that. It doesn't say, now go through all of the other vertices to make them your starting vertex. So it's only saying start at a vertex and find our best upper bound. Now, I don't know that that's, obviously the best upper bound is going to be the lowest number possible. In fact, it's going to be the Hamiltonian cycle. But we're trying to come up with an algorithm for a quite good upper bound. So we're looking for a better upper bound. It's not necessarily going to be the best. Okay, now if you repeat this though with other vertices, then you're going to find probably a better upper bound by starting at different vertices as well. Okay, let's see what it says in this box. It says completing a table of least distances converts a practical TSP into a classical TSP. Right, because in a classical TSP, traveling salesman problem, you need a complete graph to start off with. Okay, because it ensures that the graph is complete and so a Hamiltonian cycle exists. So Hamiltonian cycle is simply going to all of the vertices, but the Hamiltonian cycle is not necessarily considering the weights. Maybe I didn't mention that earlier. Okay, right. The algorithm should only be used on a complete graph. We've done that. And that satisfies the triangle inequality. Suddenly they're talking about the triangle inequality here, but that basically means which means the direct route between two adjacent vertices means the direct route between two adjacent vertices is always the shortest route. Well, we've already talked about that. We've already made the shortest route in the previous problem. Okay, let's look at this then. We've got example 11. I think I've gone on for too long here. So let's take this. So let's just take this here. Saved it earlier so I can fit it onto one page. Okay, so it says this graph shows the connections between 7 cities. A driver needs to make deliveries to all of these cities, beginning and ending in city A. So we're told in this case we need to start at A. So that's going to help us with our algorithm as well. And the weights are the driving times between the cities measured in hours. Now find the values of A, B, and C. So we can see A is A to C here. A to C, let's just choose a different color. So we've got A to C. And A to C, there's many different routes. We've got 17 there, we've got 20 there, we've got more than 17 there. Potentially we've got 20 there. We've got lots of different routes to consider. But A in this case is going to be 17. So let's just write that down to the side. So A is 17. And then for B, let's consider B. B is the route from B to E. So B to E here. And again, we've got 22 there. We've got 21 there. I think 21 is the best. Yeah, so 21. So I've just considered different routes there. So B is 21 and C for the final answer, I believe, is 19. Let's just check it through. So for C is D to E. D to E is 21 and is 19 there. So 19 is the best option. Okay, so now once we've put those numbers into here, we can see that we've got this symmetry on both sides and that this is now a table of least distances, and this is essentially describing a complete graph for lowest distances between each of the towns in this case. Okay, so by the way, sometimes in old maps you will see a table like this, right, with destinations, and that won't be there. And you'll see, cities there: Edinburgh, Birmingham, Cardiff, and you'll have the distances between each of those things as well. So there's only a need for one set of numbers there. Obviously, with the advent of Google Maps, that's kind of destroyed. Okay, just take a sip of my tea. I say we're going to do part B. Okay, so it says use the nearest neighbor algorithm beginning at town A. So let's deal with this one here. So beginning at town A, so we're going to try and find. So we don't care about anything which is in A, so we can cross those ones off. Now we're looking for the lowest number in here, which is 5. This one off because I no longer need to connect to F. F is already in a vertex which has been included. So we've got F there, and now we're at F. Different to Prim's algorithm, because in Prim's algorithm we could choose A or F to make the minimum spanning tree, and in this case we are always going from the next vertex. So we're looking in the F row here. So in F we can see this is the lowest number, so let's cross those ones out. Now we're in G, so we can see 6 is the lowest, we can cross the rest out. Now we're at E, so the lowest there is B, C, or 16. So 16 is the lowest, in fact. So we can cross those ones out. Now we're at C. And at C, 7 is the lowest, so we can cross these ones out. We're now at D. And at D, we only have one option here. We've got to choose the 16. So we now have limited options, of course. So we have to choose the 16. And now we have to complete the cycle by ending up back at A. So ending up back at A is, we're going to need to do D to A. So this is now back in play. So we need to go from, where were we? D to B, sorry. We're now at B. That was the last one which we chose. And so now we need to choose this one to get back to A. We have to get back to the beginning again. So there we go. That's an upper bound. It's not necessarily the best circuit that we can make there, but we're told where we start and finish. So it's a good upper bound that we found, potentially. It is an upper bound. I don't even know if it's good, to be honest. I mean, it could be that last value was 11,000, in which case it would be terrible. Okay, but then, so we've done that, and all we need to do for part B then is now to say, once we've done that, we should really state what the route is. So we should say, we can complete our algorithm, by the way, by just saying, where did we start with? So we went A to F, then we went F to, difficult to see now, I should have written it down at the same time. I think we went to G, and then we went G to E, and E to C, and then C to D, and then D to B, and then back to A. So that was our route, okay, and the total length of that would be all of those numbers added together. So of course we're going to need to do 5 plus, it doesn't really matter which order I add them in, 7 plus 16, plus 7 plus 16, and so on, okay, plus 7 plus 16, and so on, okay. Sorry, struggling to put that in. Okay, so that's going to give us an upper bound, but not necessarily the best route at all. Okay, now for part C, it says if the driver were to follow this route, which towns would he pass through more than once? So now you need to go back to this and think about how you got between the places. So to get from A to F was just A to F. Then from A to G, so F to G, it was just this. And then G to E was just this. And then to C, we had to choose E to C was through this route here. So then we had to go back through G and ending up in C in that case. So we went through G more than once. And then from C we went to D, which was this, and then to B. So again, we're repeating things there, and I believe that we repeated this and this. So we're going back again through C, and then from B to A completes that one there. So that was the route which we took. So you need to go back to the original graph to find the actual route which has been taken there. So he's passed through towns G and C twice. Okay, well that's that done really. I think we are done with that. There's the answers. You can see this, they've done exactly the same here as well. They've come up with the solution. So it's important to write down your solution as well. That shows that you've completed the algorithm correctly, and they've added things in order. Perhaps I should have done that as well. And they've gone with the actual route there as well. So they've listed the actual route to show that G and C are actually passed through twice. Okay, so this is the upper bound algorithm. It was called the nearest neighbor algorithm, and that enables you now to do exercise 15I. In the next exercise, we'll do a lower bound algorithm. So that's coming next. Just to recap, we talked about Hamiltonian cycles and trails. Sorry, and paths. Eulerian was trails. Hamiltonian cycles go around a network and through all vertices and end up back at the start. Hamiltonian cycles do not necessarily have the least weight, but they always exist in complete graphs. For the traveling salesman problem, we want to make our graph complete, okay, so that Hamiltonian cycles exist, and then the best that we can do for an upper bound is to use the nearest neighbor algorithm. Okay, guys, thanks for listening. One more exercise to do after this one.